Classical physics, which was primarily based on the works of Sir Isaac Newton, James Clerk Maxwell, and others, had achieved remarkable success in explaining the behavior of objects and phenomena that were large in scale and could be observed through direct experience. Newton's laws of motion and the law of universal gravitation explained the motion of planets, the trajectories of projectiles, and the forces between bodies. Maxwell's equations, on the other hand, unified electricity, magnetism, and light into a single theory of electromagnetism. These laws worked seamlessly in our everyday world and even in the vast expanse of the universe, from the motion of celestial bodies to the behavior of fluids and gases. However, as the 19th century drew to a close, certain experimental observations began to challenge the adequacy of classical physics. These issues became particularly evident when scientists started investigating phenomena that occurred at the atomic and subatomic levels. The classical laws of physics seemed to break down when applied to smaller systems or those involving high speeds or intense electromagnetic fields. These problems indicated that classical physics was incomplete and could not fully explain the workings of the universe, especially in the realm of atomic and quantum phenomena. One of the major issues classical physics encountered was the behavior of black-body radiation. A black body is an idealized object that absorbs all incident radiation and re-emits it in a characteristic spectrum. According to classical theories, a black body should radiate energy in a continuous spectrum, with higher frequencies producing more energy. This prediction was based on the principles of electromagnetism and thermodynamics, which governed the behavior of radiation as a function of temperature. However, when scientists experimentally measured the spectrum of radiation emitted by a black body at various temperatures, they found that the observed radiation pattern did not match the classical predictions. Classical physics, particularly the Rayleigh-Jeans law, predicted that the energy radiated by a black body would increase without bound as the frequency of radiation increased, which implied that a black body would emit infinite energy as the frequency approached the ultraviolet range. This was a clear contradiction, as it would imply that objects heated to high temperatures would release an unreasonably large amount of energy, a result that was not observed in reality. The failure of classical physics to explain this behavior came to be known as the ultraviolet catastrophe. The ultraviolet catastrophe was not just a theoretical inconsistency, it was an experimental discrepancy that called into question the validity of classical physics at high frequencies. This posed a significant problem for scientists at the time because it meant that the fundamental laws governing the behavior of radiation were incomplete. The inability of classical physics to account for this anomaly led to a crisis in the scientific community, with many physicists questioning the very foundations of their field. At the time, the prevailing belief in classical physics was that energy was emitted and absorbed in a continuous manner. This idea had worked well for everyday objects, where energy could be thought of as flowing smoothly and continuously, but when applied to atomic systems, this assumption no longer held true. The failure to resolve the ultraviolet catastrophe sparked a search for a new theory that could explain the behavior of radiation at the microscopic level and, more generally, the nature of energy itself. This search for a solution would eventually lead to one of the most groundbreaking theories in the history of physics, quantum mechanics. At the forefront of this revolutionary shift was Max Planck, a German theoretical physicist who had been working on the problem of black-body radiation. Planck realized that to explain the observed behavior of radiation, he needed to propose a radical idea that departed from the continuous nature of energy that classical physics held so dear. In 1900, Planck introduced a revolutionary hypothesis that energy is not emitted or absorbed continuously, as classical physics suggested, but rather in discrete packets, which he called quanta. These quanta were not infinitesimally small amounts of energy, but rather specific, measurable quantities. The amount of energy in each quantum, according to Planck's hypothesis, was directly proportional to the frequency of the radiation, with the proportionality constant being what we now call Planck's constant, denoted as h. This idea was a radical departure from classical physics, which assumed that energy could take on any value within a given range. Planck's constant, Ha, was the key to understanding the discrete nature of energy in the atomic world. By introducing this concept, Planck not only solved the black-body radiation problem, but also set the stage for the development of quantum theory, a new framework that would revolutionize our understanding of the universe. The implications of Planck's work were profound. First, it introduced the idea that energy is quantized, meaning that energy levels are discrete rather than continuous. This concept was counterintuitive to the classical view of the world, where energy seemed to flow smoothly and without limit. Second, Planck's introduction of the constant No provided a universal scale for these quantized energy levels. This constant became a fundamental aspect of quantum mechanics and a cornerstone of the theory that would come to describe the behavior of particles at the atomic and subatomic levels. What was remarkable about Planck's constant was that it was not just a theoretical concept, it had real, measurable consequences. The constant determined the size of the quanta of energy and provided a mathematical relationship that could explain a range of phenomena, from the emission of radiation by black bodies to the behavior of light as both a particle and a wave. It provided a bridge between the world of classical physics and the strange, counterintuitive world of quantum mechanics. Before Planck's work, classical physics could not explain the behavior of atoms and subatomic particles. After Planck, a new theory, quantum mechanics, emerged, which described the behavior of particles on the smallest scales. Quantum mechanics offered a fundamentally different perspective on the nature of reality. Instead of seeing particles and energy as continuous entities that could be precisely measured, quantum mechanics revealed that particles existed in discrete states, and their behavior could only be described probabilistically. Planck's hypothesis marked the beginning of a paradigm shift in physics. It shattered the foundation of classical physics by introducing the idea of quantization, which was completely foreign to the deterministic worldview of Newtonian mechanics. The success of Planck's theory in resolving the ultraviolet catastrophe was only the beginning of a larger movement that would change the course of scientific history. His constant, Ha, not only provided an explanation for black-body radiation, but also laid the groundwork for future developments in quantum mechanics, including the works of Albert Einstein, Niels Bohr, and Erwin Schrödinger, who would go on to develop the full framework of quantum theory. Thus, Planck's constant did not just resolve a single problem in classical physics. It opened the door to a new understanding of the universe. It represented the first step in the development of quantum mechanics, which would eventually replace classical physics as the dominant theory for describing the behavior of particles at the atomic and subatomic levels. Planck's work marked a turning point in the history of science, demonstrating that classical physics, while successful in many respects, was not capable of fully explaining the complexities of the microscopic world. The significance of Planck's constant and the theory of quantum mechanics that followed cannot be overstated. It has not only provided an accurate description of the behavior of matter and energy at the smallest scales, but has also led to a multitude of technological advancements, from semiconductors and lasers to quantum computing and telecommunications. The quantum revolution, ignited by Planck's radical ideas, continues to shape the future of science and technology, making it one of the most important breakthroughs in the history of physics. The advent of Max Planck's quantum theory, fueled by his introduction of Planck's constant, marked the beginning of the quantum revolution, fundamentally altering the course of physics. This shift in scientific understanding would gradually dismantle the very foundation of classical physics and reshape how we viewed the universe at its most fundamental levels. The implications of Planck's ideas were profound, extending beyond the resolution of the blackbody radiation problem and leading to the birth of an entirely new realm of physics known as quantum mechanics. To understand the magnitude of Planck's contribution, it's essential to examine the core aspects of his hypothesis and the context within which it emerged. Before Planck's work, the prevailing theories about energy and radiation were deeply rooted in the classical view, which followed continuous models of physical phenomena. Classical physics held that energy could be distributed in an infinite number of ways and could change continuously over time. This continuity worked exceptionally well for large-scale phenomena, where objects like planets and projectiles followed predictable, smooth paths governed by Newtonian mechanics. However, this understanding fell apart when applied to atomic and subatomic systems, where the continuous nature of classical physics could not explain many experimentally observed phenomena. One such example was the issue of black body radiation. Classical physics, using Rayleigh-Jean's law, predicted that the intensity of radiation emitted by a black body would increase indefinitely as the frequency of radiation increased, leading to the ultraviolet catastrophe. In reality, however, the observed radiation spectrum was vastly different, with a peak at a certain frequency and a rapid fall-off as frequency increased. The ultraviolet catastrophe highlighted the inability of classical physics to explain the behavior of energy at small scales, particularly when objects reached high frequencies. The failure to explain this behavior within the confines of classical physics led to a crisis, and Planck's breakthrough came as an attempt to resolve this dilemma. Planck's key insight was that energy does not radiate in a continuous flow but rather in discrete quantities or packets, which he termed quanta. These quanta were not arbitrarily small, they had a fixed relationship to the frequency of radiation. Specifically, the energy of a quantum was proportional to the frequency of the radiation, with Planck's constant serving as the proportionality factor. This idea was completely at odds with classical thinking, which treated energy as something that could vary continuously. By proposing that energy could only exist in specific quantized amounts, Planck introduced the fundamental idea of quantization into physics, which would later become one of the pillars of quantum mechanics. The introduction of Planck's constant, h, and the quantization of energy marked a significant departure from the smooth, continuous nature of classical physics. In classical physics, energy could take on any value within a given range. But with the advent of Planck's hypothesis, energy was now constrained to specific values based on its frequency. The constant, h, essentially set a threshold for the smallest possible unit of energy exchange in the microscopic world, offering a new scale that was crucial for understanding atomic and subatomic interactions. It was a concept that had no counterpart in classical mechanics, where no such discrete limits existed for energy. This quantization of energy was not a mere mathematical curiosity, it had real physical consequences that could be observed experimentally. The most famous of these consequences was the photoelectric effect, which Albert Einstein famously explained in 1905. The photoelectric effect occurs when light strikes a metal surface and ejects electrons from the surface. Classical physics predicted that the energy of the ejected electrons should be proportional to the intensity of light, but experiments showed that only light of a certain frequency could eject electrons, regardless of its intensity. This behavior could not be explained by classical wave theories of light, but Planck's idea of quantized energy, and Einstein's extension of it to light as photons, provided a simple and accurate explanation for the phenomenon. Einstein's work on the photoelectric effect, which earned him the Nobel Prize, further solidified the validity of Planck's quantum hypothesis. One of the most revolutionary aspects of Planck's theory was that it did not just apply to radiation or energy emission, it had broad implications for the nature of light itself. Classical physics had treated light solely as a wave, governed by electromagnetic theory. Planck's work, along with Einstein's interpretation, introduced the concept of light being both a wave and a particle, what we now call wave-particle duality. Light, in this new framework, could be described not only by its wave properties, but also by its particle-like properties, with each particle of light, or photon, carrying an energy proportional to its frequency. This duality was one of the most profound departures from classical physics and became a central feature of quantum mechanics. The introduction of Planck's constant also laid the groundwork for the development of quantum mechanics. Niels Bohr, for example, used Planck's ideas to explain the discrete energy levels of electrons in atoms. Bohr's model of the atom, which suggested that electrons could only occupy certain orbits or energy levels, was based on the quantization of energy that Planck had introduced. Later, Erwin Schrödinger's wave mechanics and Werner Heisenberg's uncertainty principle would further expand upon the foundations laid by Planck and Bohr, culminating in the full-fledged quantum theory that governs the behavior of particles at the smallest scales. In addition to its foundational role in quantum mechanics, Planck's constant has had practical applications in numerous fields, from semiconductor technology and quantum computing to spectroscopy and astrophysics. The precise value of .h is critical in calculations that involve atomic interactions, such as in the behavior of atoms in a gas, the properties of materials at low temperatures, and the interactions between light and matter. The constant is also essential in the calculation of energy levels in atoms, the emission spectra of molecules, and the calculation of thermodynamic properties at quantum scales. Planck's constant, in essence, provided the key to understanding the quantum world. It symbolized the shift from the deterministic and continuous worldview of classical physics to the probabilistic and discrete nature of quantum mechanics. By introducing HA, Planck helped unravel a new dimension of reality, one that was both strange and paradoxical compared to classical expectations. The implications of his work reverberated throughout the 20th century, contributing to the most successful theory of physics to date, quantum mechanics, and laying the foundation for much of the technology and understanding that defines our modern world. The legacy of Planck's constant cannot be overstated. It remains one of the fundamental constants of nature, central to the functioning of quantum theory, and a cornerstone of modern physics. His groundbreaking work, which began as a solution to a specific problem in black-body radiation, ultimately transformed the landscape of physics, illustrating how a single scientific breakthrough can completely change our understanding of the universe. Planck's constant forever altered the path of science, bridging the classical world of determinism with the probabilistic world of quantum mechanics and providing a new lens through which we continue to explore the mysteries of nature at the smallest scales. Max Planck's introduction of the constant that bears his name was not just a solution to a single theoretical problem, it was the key that unlocked the door to a new era in physics, one that would radically transform our understanding of the universe. The impact of Planck's constant on both theoretical and experimental physics was profound, making it clear that classical physics was not sufficient to describe the behavior of energy and matter at microscopic scales. To fully appreciate the revolutionary nature of Planck's contribution, it's important to understand the context in which his work emerged and the profound implications it had for the nature of light, energy, and ultimately, the entire physical world. Before Planck's work, classical physics had an almost perfect track record when applied to macroscopic objects, those that we encounter in everyday life. Newton's laws of motion governed the movement of planets and projectiles. Maxwell's equations beautifully described the interaction of electric and magnetic fields, and the laws of thermodynamics explained the behavior of gases and energy exchanges. However, as scientists began to probe smaller and smaller scales, the assumptions that had worked so well at the macroscopic level began to fail. One of the most glaring failures came when scientists tried to understand the radiation emitted by heated objects, a problem that was central to Planck's work. The phenomenon of blackbody radiation had been puzzling scientists for some time. A blackbody, by definition, absorbs all incoming radiation and then re-emits that energy in the form of light or heat. The spectrum of this radiation depends on the temperature of the object, but classical physics, using the Rayleigh-Jeans law, predicted that the intensity of emitted radiation would continue to increase without bound as the frequency of the radiation increased. This prediction, which suggested that an object would emit infinite energy at higher frequencies, was clearly at odds with reality, where only a finite amount of energy was emitted. This discrepancy, known as the ultraviolet catastrophe, pointed to a fundamental flaw in classical physics. The failure to explain the radiation spectrum of a black body indicated that the classical understanding of energy emission, based on the idea that energy could vary continuously, was insufficient for explaining phenomena at very small scales. What was needed was a new way of thinking about energy, one that could account for the discrete nature of the behavior at microscopic levels. Enter Max Planck, who, in 1900, introduced a radical new idea to address this problem. Planck proposed that energy is not emitted or absorbed in a continuous manner, as classical physics had assumed, but rather in discrete packets, or quanta. This suggestion was a bold departure from the long-standing view that energy was a continuous entity. Planck's idea was that energy could only be exchanged in specific amounts, and this quantization of energy would be fundamental to understanding the behavior of light and matter at atomic and subatomic scales. To explain the quantization of energy, Planck introduced a proportionality constant, which became known as Planck's constant. The relationship he proposed was simple. The energy of a quantum of radiation is proportional to the frequency of the radiation, with the constant, HA, being the factor of proportionality. This equation, E equals hc.f, where E is the energy of the quantum, h Planck's constant, and F is the frequency of the radiation, provided a direct relationship between the frequency of light and the energy of the quantum. The implications of this idea were far-reaching. By quantizing energy, Planck was able to resolve the ultraviolet catastrophe and explain the observed blackbody radiation spectrum. More importantly, Planck's introduction of the constant Ht provided the first hint that the classical picture of the universe, one in which energy and matter could take any value along a continuous spectrum, was incomplete. Planck's constant represented a boundary, a threshold below which the continuous assumptions of classical physics no longer applied. Instead, the universe at small scales operated in discrete units, not smooth flows. This notion of quantized energy was difficult for many physicists to accept initially. The idea that energy could only exist in specific, discrete packets seemed counterintuitive, especially in a world governed by the continuous laws of classical physics. However, as more experimental evidence accumulated, it became clear that Planck's ideas were not just theoretical curiosities. They provided an accurate description of nature at the atomic and molecular level. Planck's constant became an indispensable tool for explaining the behaviors of particles, atoms, and light. The next breakthrough came in the early 20th century, with Albert Einstein's work on the photoelectric effect. In 1905, Einstein used Planck's quantization idea to explain why light of a certain frequency could cause the ejection of electrons from a metal surface, while light of lower frequencies would not, regardless of its intensity. Classical physics, which treated light as a continuous wave, could not explain this phenomenon. But Planck's hypothesis, extended by Einstein, showed that light, while exhibiting wave-like properties, also behaved as if it were composed of discrete particles, now called photons, with energy proportional to the frequency of the light. Einstein's explanation of the photoelectric effect was another step in the dismantling of classical physics. It demonstrated that light was not purely a wave, as had been previously thought, but also had particle-like characteristics. This insight, building on Planck's work, was one of the first major pieces of evidence for what would become known as wave-particle duality, the idea that light and other forms of radiation can exhibit both wave-like and particle-like behavior depending on the circumstances. Einstein's work earned him the Nobel Prize in 1921, and his interpretation of the photoelectric effect would become one of the foundational principles of quantum mechanics. At this point, the foundations of quantum mechanics had been laid, but the full picture of the quantum world was still incomplete. Other physicists, such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, would expand upon Planck's ideas to develop a comprehensive theory of quantum mechanics. Bohr, for example, applied the concept of quantization to the energy levels of electrons in atoms, explaining the discrete spectra observed in atomic emission lines. Heisenberg and Schrödinger would develop the mathematical framework of quantum mechanics, with Heisenberg's uncertainty principle and Schrödinger's wave equation providing key insights into the behavior of particles on the smallest scales. In the decades following Planck's work, quantum mechanics grew into a fully developed theory, one that would revolutionize not only physics but also many other fields, from chemistry and materials science to electronics and computing. The advent of quantum theory, made possible by Planck's constant, has led to numerous technological advancements, from the development of lasers and semiconductors to the modern field of quantum computing. Today, Planck's constant remains a central part of quantum theory, and its value is fundamental to understanding the energy scales at which quantum effects become significant. Max Planck's work shattered the foundations of classical physics, revealing a new world of discrete energy levels and probabilistic behavior. The constant, h, introduced to describe these quanta, became one of the most important constants in nature, setting the scale for quantum effects. Planck's contributions to the field of physics marked the beginning of the quantum age, and his ideas continue to shape our understanding of the universe at the smallest scales. Quantum mechanics, made possible by Planck's constant, is the most successful physical theory to date, and it has opened up new avenues of research and technological innovation that were unimaginable in the classical era. Max Planck's introduction of the constant that bears his name, Planck's constant represented more than just a theoretical solution to the problem of blackbody radiation. It marked the dawn of a new era in physics, fundamentally altering how scientists viewed the nature of energy, light, and matter. His work initiated the transition from classical to quantum physics, a shift that would fundamentally change our understanding of the universe. To comprehend the full significance of Planck's constant, we need to explore the ripple effects of his work on both theoretical physics and the real-world applications it enabled. Before Planck's insight, classical physics had been extraordinarily successful in explaining the behavior of large-scale phenomena, ranging from the motion of celestial bodies to the behavior of fluids and gases. The laws of motion formulated by Isaac Newton, for example, could accurately predict the motion of planets and projectiles, while James Clerk Maxwell's equations unified electricity, magnetism, and light into a single theoretical framework. However, as scientists delved deeper into the study of matter on smaller scales, especially the behavior of light and energy at the atomic level, classical physics began to show significant cracks. Classical theories, particularly those based on continuous models of energy, failed to explain phenomena at the microscopic level. The most glaring of these was the inability to resolve the issue of blackbody radiation. Blackbody is an idealized object that absorbs all incident radiation and re-emits it in a characteristic spectrum. According to classical physics, a black body should radiate energy in a continuous spectrum with an ever-increasing intensity as the frequency of radiation increases. This prediction, known as the **Rayleigh-Jeans law, was later shown to predict an infinite amount of energy at higher frequencies, a result that was physically absurd. The phenomenon was called the **ultraviolet catastrophe, ***, and it highlighted the inadequacy of classical physics when dealing with high-energy, short-wavelength radiation. Planck's proposal to solve this problem was both simple and radical. He suggested that the energy emitted by a black body was not continuous, as classical physics had assumed, but rather discrete, existing in quantized amounts. This was an entirely new way of thinking. Planck introduced the concept of energy quanta ***, small, indivisible packets of energy that could only take specific values. He formulated the relationship between the energy of a quantum and the frequency of the radiation, expressing it mathematically as E equals HA.F, where ek is the energy of the quantum, h is Planck's constant and F is the frequency of the radiation. This equation was revolutionary. It indicated that energy is not spread out in a continuous spectrum, but rather exists in discrete chunks. Planck's constant, h, was the proportionality factor that set the scale of these quanta, providing the first real physical clue that the universe operated on a fundamentally discrete, rather than continuous, basis at the atomic scale. Planck's introduction of H provided a mathematical framework to accurately describe the blackbody radiation spectrum, resolving the ultraviolet catastrophe once and for all. It was also the first step in a broader rethinking of the nature of energy and matter. For the first time, physicists were forced to confront the idea that energy did not flow continuously, but was rather chunked in fixed units. This discrete view of energy was completely foreign to the classical intuition that had governed physics for centuries. The immediate impact of Planck's work was limited, as the full implications of his theory were not fully realized at the time. However, Planck's constant would go on to play a central role in the development of quantum mechanics, a new framework that would fundamentally change how we understood the behavior of particles at the smallest scales. The next major development came with Albert Einstein, who, in 1905, used Planck's ideas to explain the photoelectric effect, another phenomenon that classical physics could not account for. The photoelectric effect occurs when light shines on a metal surface, causing the ejection of electrons from that surface. According to classical physics, the energy of the ejected electrons should be proportional to the intensity of the light, with brighter light ejecting more electrons. However, experiments showed that only light of a certain frequency, regardless of intensity, could cause the ejection of electrons. This discrepancy was another puzzle for physicists. Einstein proposed that light, which was traditionally understood as a wave, could also be understood as being composed of particles called photons. These photons carried energy proportional to the frequency of the light, according to Planck's relationship. Einstein's explanation of the photoelectric effect, which incorporated Planck's quantum hypothesis, was a key breakthrough. Einstein showed that light was not only a wave, but also exhibited particle-like properties, a duality that would become a cornerstone of quantum theory. This dual nature of light-wave-particle duality was a critical step in the development of quantum mechanics. Einstein's work on the photoelectric effect was foundational, earning him the Nobel Prize in 1921 and solidifying Planck's ideas in the process. The photoelectric effect demonstrated that light, as well as energy in general, cannot be treated as a purely continuous entity. Planck's constant became an essential part of the theoretical framework that described the nature of energy exchanges at the atomic level. Through this lens, the continuous world of classical physics was revealed to be a special case, while the behavior of matter and energy on the smallest scales was governed by the rules of quantum mechanics. With the growing acceptance of Planck's quantum hypothesis, other physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, built upon this foundation to develop the complete structure of quantum theory. Bohr, for instance, applied the concept of quantized energy to the orbits of electrons in atoms, explaining the discrete spectral lines observed in atomic emission spectra. Bohr's model of the atom used Planck's idea of quantized energy levels to describe the structure of atoms, particularly the hydrogen atom. Over time, quantum mechanics expanded far beyond Planck's initial work, but his constant remained a critical part of the theory. It was incorporated into Heisenberg's uncertainty principle and Schrödinger's wave mechanics. Planck's constant thus became the cornerstone of the quantum world, the bedrock on which the entire theory was built. It is no exaggeration to say that without Planck's constant, the quantum revolution would not have occurred. The legacy of Planck's constant extends far beyond the development of quantum mechanics. It has led to an unprecedented array of technological advancements. Planck's insights into quantization have paved the way for the development of semiconductors, the foundation of modern electronics. Quantum mechanics, based on Planck's constant, has led to the invention of lasers, the development of transistors, and the creation of technologies like MRI machines, and quantum computers, These technologies have transformed virtually every aspect of modern life, from communication and computing to medicine and energy. Today, Planck's constant is not just a theoretical concept, it is an essential part of modern physics and technology. It remains one of the most important constants in nature, appearing in countless equations that govern the behavior of particles, atoms, and energy. It symbolizes the departure from the deterministic, continuous world of classical physics and the entrance into the probabilistic, quantized realm of quantum mechanics. The world we live in today, governed by quantum technologies, is a direct result of Max Planck's groundbreaking ideas and the introduction of his constant. In summary, Planck's constant was not just the solution to a single problem in theoretical physics. It represented the key to understanding the atomic and subatomic worlds, where energy and matter behave in fundamentally different ways than our everyday experiences suggest. Planck's work, building on earlier discoveries in thermodynamics and electromagnetism, gave rise to the field of quantum mechanics, a theory that has revolutionized physics and led to the creation of technologies that define the modern world. Planck's constant continues to shape our understanding of the universe, from the microscopic to the macroscopic, making it one of the most important constants in all of science. Max Planck's introduction of his constant, denoted as h, was not only a pivotal moment in the history of physics, but also the starting point of a paradigm shift that would change our fundamental understanding of the universe. The constant, initially introduced to resolve the problem of blackbody radiation, served as the key that unlocked the mysteries of the quantum world. Planck's work marked the beginning of quantum mechanics, a revolution in science that would profoundly influence not only physics, but also chemistry, technology, and even the way we perceive reality itself. To fully appreciate the significance of Planck's constant, it's essential to understand its context, its profound implications, and the transformations it sparked in scientific thought. Before the 20th century, classical physics was largely based on the deterministic and continuous nature of the physical world. The laws of motion developed by Isaac Newton were successfully applied to describe the motion of celestial bodies and the behavior of everyday objects. James Clerk Maxwell's equations unified electricity, magnetism, and light into a single theoretical framework that was essential for understanding electromagnetism. Classical physics appeared to explain all phenomena at large scales, and, for centuries, it seemed that these theories would remain sufficient for understanding the physical universe. However, as scientists began to explore the behavior of light and matter at very small scales, they found that classical physics no longer provided satisfactory explanations. One of the most pressing issues in classical physics at the time was the behavior of radiation emitted by heated objects. This phenomenon, known as black body radiation, had been the subject of intense study, but classical physics could not explain it. A black body is an idealized object that absorbs all incident radiation and re-emits it in a characteristic spectrum. According to classical theories, a black body would radiate energy in a continuous spectrum, with the intensity of radiation increasing as the frequency of radiation increased. This prediction, however, led to the so-called ultraviolet catastrophe, the prediction that a black body would emit infinite energy at high frequencies. This was clearly unphysical, as no object could emit infinite energy, and it demonstrated that classical physics had limitations when applied to high-frequency radiation. The ultraviolet catastrophe was not a theoretical quirk but a glaring experimental discrepancy. When scientists tried to measure the radiation emitted by black bodies at various temperatures, they found that the actual radiation emitted followed a different pattern from the one predicted by classical physics. Specifically, the intensity of radiation peaked at a certain frequency and then dropped off rapidly at higher frequencies. The failure of classical physics to explain this discrepancy represented a crisis for scientists, as it revealed that the existing framework could not account for the behavior of matter at small scales. The turning point came when Max Planck, a German physicist, proposed a radical new idea. Rather than continuing to treat energy as a continuous quantity, as classical physics had, Planck suggested that energy is quantized. This means that energy is not emitted or absorbed in a smooth, continuous manner, but instead exists in discrete units or packets, which Planck called quanta. This was an astonishing departure from classical thinking, where energy could vary continuously along any scale. Planck's idea was based on the observation that the energy emitted by a black body at different temperatures was best described not by a continuous distribution, but by a set of discrete values, each corresponding to specific amounts of energy. To quantify this new concept, Planck introduced the quantum hypothesis, and formulated the relationship between the energy of a quantum and the frequency of radiation. The energy, E, of a quantum, Planck proposed, is proportional to the frequency, F, of the radiation, with the proportionality constant being Planck's constant, denoted by H. The equation became E equals H CDOF, where E is the energy of the quantum, H is Planck's constant, and F is the frequency of the radiation. This was the first appearance of HA, a constant that would become one of the most important values in all of physics. The introduction of Planck's constant solved the problem of blackbody radiation by explaining the observed radiation spectrum. It also marked the beginning of a new chapter in physics, one in which energy and matter would be understood as existing in discrete units rather than continuous flows. Planck's idea, while revolutionary, was initially met with skepticism. The notion that energy could only exist in discrete packets was difficult to accept, as it was completely contrary to the smooth, continuous world described by classical physics. However, Planck's hypothesis was not just a theoretical insight, it was validated by experimental data. As more research was conducted, it became clear that the behavior of energy, particularly in atomic and molecular systems, could not be explained without invoking Planck's quantization. Over time, this discrete view of energy became widely accepted, and Planck's constant was recognized as one of the fundamental constants of nature. The full implications of Planck's work were realized only later, as other physicists expanded on his ideas. In 1905, Albert Einstein used Planck's concept of quantized energy to explain the photoelectric effect. In the photoelectric effect, light striking a metal surface causes the emission of electrons. Classical physics predicted that the energy of the emitted electrons should depend on the intensity of the light, but experiments showed that only light of a certain frequency could cause the emission of electrons. Einstein's explanation, which built upon Planck's quantum hypothesis, proposed that light is made up of discrete particles called photons. Each photon carries energy proportional to its frequency, in accordance with Planck's relation. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921, further cementing the importance of Planck's constant in understanding the nature of light. This discovery of wave-particle duality the idea that light exhibits both wave-like and particle-like behavior was another major departure from classical physics. Planck's constant played a central role in this realization, as it was through the quantization of energy that the dual nature of light was revealed. The understanding that energy exists in discrete packets opened the door to a new way of thinking about light and matter. It also provided the foundation for the development of quantum mechanics, a theory that would later describe the behavior of particles at the atomic and subatomic scales. Quantum mechanics, which emerged in the early 20th century, is based on the fundamental idea that energy is quantized and that particles do not have definite positions and velocities until they are observed. This uncertainty and probabilistic nature of particles were encapsulated in Heisenberg's uncertainty principle, Schrödinger's wave equation, and other key developments that followed. Quantum mechanics became the dominant theory of matter and energy at the microscopic level, and Planck's constant was central to this theory. Today, Planck's constant is not just an abstract idea in theoretical physics, it has real-world implications in a variety of fields. It plays a crucial role in the functioning of semiconductors, which are the backbone of modern electronics. Planck's constant is also involved in the operation of lasers, MRI machines, and other advanced technologies. Moreover, it is fundamental to the study of quantum computing which promises to revolutionize the field of computation by using quantum bits, or qubits, to perform calculations far more efficiently than classical computers. The impact of Planck's constant extends far beyond the realm of physics. Its introduction, along with the broader quantum theory, has led to significant advancements in technology, medicine, and materials science. The development of technologies such as quantum cryptography, superconductivity, and nanotechnology. Is directly linked to the principles of quantum mechanics, which are built on the foundation laid by Planck's work. In conclusion, the introduction of Planck's constant marked the end of classical physics dominance and the beginning of the quantum era. By quantizing energy and introducing the concept of energy quanta, Planck solved the black-body radiation problem and provided the theoretical framework for the development of quantum mechanics. The constant, H became the cornerstone of this new theory, which revolutionized our understanding of the universe at the atomic and subatomic levels. Planck's contributions were instrumental in the development of technologies that define modern life, from semiconductors to quantum computing. Today, his constant remains a fundamental element of the physics that governs the behavior of energy and matter at the smallest scales, and its legacy continues to shape the future of science and technology. Max Planck's introduction of his constant, which revolutionized the understanding of energy, set in motion a fundamental change in how we perceive the behavior of matter and energy. Prior to Planck's work, classical physics governed much of the observable world with its deterministic, continuous views of motion, energy, and light. However, the microscopic world, where the rules of classical physics no longer seemed to apply, required a new framework. Planck's constant became the key that unlocked the strange and counterintuitive realm of quantum mechanics. His work not only resolved a long-standing issue in theoretical physics, but also paved the way for developments that would shape the future of science and technology. The nature of light, energy, and matter was forever changed through the introduction of Planck's constant, offering a fresh understanding of the universe at the atomic and subatomic levels. The main issue that sparked Planck's groundbreaking discovery was the failure of classical physics to explain black body radiation. A black body is an idealized physical object that absorbs all incident radiation and re-emits it in a characteristic way. Classical theories, specifically the Rayleigh-Jeans law, predicted that the intensity of radiation would continue to increase as the frequency of the emitted radiation grew, leading to an absurd result known as the ultraviolet catastrophe. According to classical physics, this would imply that a black body would emit infinite energy at higher frequencies, a conclusion that was clearly unphysical and contradicted experimental observations. The intensity of radiation did not increase indefinitely, but followed a predictable pattern with a peak at a specific frequency, after which it decreased. This problem exposed a fundamental flaw in classical physics, which was based on the assumption that energy could vary continuously. Energy, in the classical world, was considered a fluid flowing smoothly from one state to another. Yet, when applied to the atomic level, this continuous model no longer worked. The energy emitted by a black body at different temperatures could not be explained by classical theories alone, and thus physicists were faced with the realization that something more fundamental was needed to explain these observations. Max Planck, who was working on the problem of black body radiation, proposed a revolutionary hypothesis in 1900 that would alter the course of physics. Rather than continuing with the classical view that energy could be emitted in a continuous manner, Planck suggested that energy could only be emitted or absorbed in discrete units, which he called quanta. In other words, the flow of energy was not continuous, but quantized. This was an incredibly bold step, as it directly challenged the well-established principles of classical physics. Planck's insight came at a time when physicists were grappling with how to understand phenomena at the microscopic level, and his quantization of energy provided a solution. To formalize this idea, Planck introduced the now famous Planck's constant denoted h, which would serve as the proportionality constant between the energy of a quantum and the frequency of radiation. The equation that Planck proposed to explain the relationship was E equals hc.f, where E is the energy of the quantum, F is the frequency of the radiation, and h is Planck's constant. This equation revealed that the energy of a quantum was directly proportional to the frequency of the radiation, with Planck's constant as the proportionality factor. The introduction of this constant was pivotal because it provided a mathematical framework that could explain the previously unexplainable black body radiation spectrum. The energy of radiation could no longer take any arbitrary value. It was constrained to certain discrete values, each of which corresponded to a specific frequency of radiation. At the heart of Planck's discovery was the realization that energy, in the realm of atoms and subatomic particles, behaves differently than energy in the macroscopic world described by classical physics. While classical physics had worked well for large objects like planets and moving projectiles, it was inadequate when it came to explaining phenomena at the atomic scale. Planck's work revealed that the rules governing energy at small scales were governed by fundamentally different principles, ones that could not be captured by classical physics. This shift from a continuous to a discrete understanding of energy was a radical departure from the established worldview. Though Planck's ideas were initially met with resistance, they soon found support from experimental evidence. The success of Planck's theory in resolving the ultraviolet catastrophe helped solidify his hypothesis. What's more, Planck's work opened up a new path of exploration for understanding the behavior of particles and waves at the microscopic level. In the years following Planck's discovery, a series of breakthroughs would further solidify the importance of his constant, including Albert Einstein's work on the photoelectric effect and Niels Bohr's model of the atom. In 1905, Einstein applied Planck's quantum theory to explain the photoelectric effect which occurs when light strikes a metal surface and causes the ejection of electrons. Classical physics, which treated light as a continuous wave, had trouble explaining why only light of a certain frequency could cause electrons to be ejected, regardless of the intensity of the light. Einstein proposed that light, in addition to being a wave, could also be considered as being composed of particles, or photons, and that each photon carried energy proportional to the frequency of light. This breakthrough was directly inspired by Planck's work and demonstrated that energy was quantized at the level of light itself. Einstein's explanation of the photoelectric effect earned him the Nobel Prize in 1921 and cemented the idea that energy behaves in discrete units, not continuous flows. The concept of energy quanta and Planck's constant soon became integral to the development of quantum mechanics which was formally developed in the 1920 seconds by physicists like Bohr, Werner Heisenberg, and Erwin Schrödinger. Bohr's model of the atom, which described electrons orbiting the nucleus in discrete energy levels, relied on Planck's quantization of energy. Bohr's model of the atom used Planck's constant to describe the allowed energy states of electrons in hydrogen atoms. This marked another key development in the application of Planck's ideas, as it explained the discrete spectral lines observed in atomic emission spectra. Quantum mechanics, born from Planck's constant, became the new framework for understanding atomic and subatomic phenomena. The implications of Planck's constant extended far beyond theoretical physics. The development of quantum mechanics gave rise to groundbreaking technologies, many of which have become central to modern life. Semiconductors which form the basis of modern electronics, rely on the principles of quantum mechanics. Lasers, which are ubiquitous in fields ranging from telecommunications to medicine, operate on principles derived from quantum mechanics. Planck's constant is also central to the study of quantum computing, which promises to revolutionize the field of computation by using quantum bits, qubits, to perform calculations exponentially faster than classical computers. Beyond these technological advances, Planck's constant has influenced many areas of modern science. It plays a crucial role in understanding the behavior of atoms and molecules, the formation of chemical bonds, and the behavior of materials under different conditions. It is also foundational in the study of quantum field theory, which provides the framework for understanding the interactions of particles and fields in the universe. Planck's constant is involved in the calculations of quantum entanglement, and quantum superposition, phenomena that challenge our intuitions about reality and have applications in quantum communication and encryption. In conclusion, Planck's constant was a revolutionary idea that transformed the field of physics and set the stage for the development of quantum mechanics. Through the introduction of energy quanta and the realization that energy exists in discrete units, Planck opened the door to a new understanding of the universe at its most fundamental levels. His work laid the groundwork for some of the most significant advancements in modern science and technology, shaping the way we understand the behavior of light, matter, and energy. Planck's constant, though initially met with resistance, became one of the most important constants in all of science, and its legacy continues to influence the direction of research and technological innovation today. Max Planck's introduction of his constant, h', is widely considered one of the most profound developments in the history of physics. His work fundamentally reshaped the way we understand the nature of energy and matter, providing the foundation for quantum mechanics. Planck's constant, initially proposed to solve the problem of blackbody radiation, is now a cornerstone of modern physics. The significance of HA lies not just in its ability to resolve theoretical discrepancies, but in how it paved the way for a new understanding of the microscopic world, where particles and energy behave in ways that classical physics could not explain. The development of the quantum hypothesis began with Planck's recognition of the shortcomings of classical physics in explaining the observed spectrum of radiation emitted by heated objects, known as blackbody radiation. Classical physics predicted that a black body would emit infinite energy as its temperature increased, which led to the ultraviolet catastrophe. This flaw in classical predictions contradicted experimental observations, which showed that energy emission from a black body increased with temperature but did not approach infinity. In response to this, Planck introduced the idea that energy could not be emitted or absorbed continuously, but rather in discrete packets, or quanta. This was a radical departure from the continuous nature of energy described by classical physics. Planck's equation, E equals hc.f, where E is the energy of a quantum, h is Planck's constant, and f is the frequency of the radiation, was a breakthrough. It revealed that energy is quantized, meaning it exists in fixed amounts rather than flowing smoothly. This idea was counterintuitive at the time, as classical physics had long held that energy was continuous and could vary smoothly across any range. Planck's constant provided the proportionality factor that determined how energy is distributed in these discrete quantities. The concept of quantization revolutionized our understanding of the atomic world and marked the beginning of quantum mechanics. The success of Planck's theory was confirmed when it accurately explained the observed spectrum of blackbody radiation, something that classical physics had failed to do. Planck's constant became essential for explaining the behavior of radiation, light, and matter at atomic scales. Planck's work paved the way for future discoveries, particularly the development of quantum mechanics. The notion that energy could exist only in discrete packets became a central principle of quantum theory, which further explored the behavior of particles and light on the atomic level. Quantum mechanics, which emerged over the next few decades, fundamentally changed our understanding of physics, introducing concepts such as wave-particle duality, uncertainty, and probability. Planck's constant also played a crucial role in explaining phenomena that classical physics could not. One of the most important was the photoelectric effect explained by Albert Einstein in 1905. The photoelectric effect showed that light previously thought to be solely a wave, could also exhibit particle-like behavior. This dual nature of light was described by Einstein using Planck's concept of quantized energy. The photoelectric effect demonstrated that light, like all energy, could only exist in discrete packets, or photons, whose energy was proportional to the frequency of the light. Einstein's work was instrumental in establishing the concept of wave-particle duality and further confirming the correctness of Planck's quantum theory. In summary, Planck's constant was not just a solution to a specific problem but a doorway to a new world of physics. It provided the necessary foundation for quantum mechanics, which would go on to explain the behavior of energy and matter at the atomic and subatomic scales. Planck's introduction of quantization was a radical shift away from classical continuous theories and led to the development of ideas such as wave-particle duality, uncertainty, and quantum field theory. Today, Planck's constant remains an essential constant in the scientific world, foundational to technologies ranging from semiconductors to quantum computing, and a reminder of the deep connection between theory and experiment in the progress of scientific discovery. Max Planck's work in introducing the concept of quantized energy and his constant, h, marks one of the most groundbreaking moments in the history of physics. His theory was revolutionary not just because it solved the issue of black-body radiation, but because it laid the foundation for an entirely new way of thinking about energy and matter. Before Planck's work, classical physics dominated the field, offering an elegant explanation of physical phenomena in terms of continuous energy. However, as scientists delved deeper into atomic and subatomic systems, classical models began to fail. Planck's introduction of his constant, h, and his idea of energy quanta offered a breakthrough that shifted the scientific community's understanding of the universe. The key issue that Planck addressed was the behavior of radiation emitted by a black body, an idealized object that absorbs all incident radiation and emits energy according to its temperature. Classical physics, specifically the Rayleigh-Jeans law, predicted that the intensity of radiation would increase without bound at higher frequencies, resulting in the ultraviolet catastrophe. However, experiments revealed that blackbody radiation did not follow this prediction. Instead, the radiation spectrum peaked at a certain frequency and fell off at higher frequencies, which contradicted classical expectations. This discrepancy signaled the limitations of classical theories, and the ultraviolet catastrophe stood as a major obstacle in understanding radiation. To solve this problem, Planck proposed that energy is not emitted or absorbed continuously, but instead in discrete packets, which he termed **quanta***. This was a revolutionary idea, as classical physics had long treated energy as a smooth, continuous entity. Planck's hypothesis suggested that energy levels could only take specific, quantized values. To quantify this idea, Planck introduced his now famous constant, HA, to describe the relationship between the energy of a quantum and the frequency of the radiation. The equation E equals hc.f, where E is the energy of the quantum, F is the frequency of the radiation, and H is Planck's constant, provided a new framework for understanding energy exchanges at the atomic scale. Planck's introduction of his constant marked the birth of quantum mechanics. It was the first time in history that energy was understood to exist in discrete units, or quanta. This idea fundamentally changed how physicists thought about the physical world, particularly at the microscopic level. Whereas classical physics had suggested that energy could be continuous and arbitrarily small, Planck's constant imposed a minimum unit of energy. This change was revolutionary because it provided the first clue that the laws governing the atomic world were different from those governing larger objects, which could be described accurately by classical physics. The success of Planck's theory was immediately evident when it accurately explained the blackbody radiation spectrum. By quantizing the energy levels, Planck solved the ultraviolet catastrophe and provided a mathematical framework that agreed with experimental observations. However, the broader implications of his work would take years to fully unfold. While Planck himself did not immediately recognize the full scope of his discovery, his constant became a critical element in the development of quantum mechanics by other physicists, including Albert Einstein and Niels Bohr. Einstein, for example, used Planck's quantization concept to explain the photoelectric effect showing that light behaved as both a wave and a particle. This discovery was instrumental in establishing the dual nature of light, a concept that would become one of the cornerstones of quantum theory. Moreover, Planck's work laid the groundwork for the eventual development of quantum mechanics a theory that would explain the behavior of particles at the smallest scales. This theory would soon describe the behavior of electrons in atoms, leading to the development of Bohr's atomic model and Heisenberg's uncertainty principle. In these ways, Planck's constant became the cornerstone of a new scientific framework, one that would go on to revolutionize not only physics, but also chemistry, materials science, and technology. The quantization of energy, made possible by Planck's constant, was fundamental to the development of technologies such as lasers, semiconductors, and quantum computers. In conclusion, Planck's constant and the introduction of quantized energy were pivotal in breaking down the classical view of the physical world. By proposing that energy exists in discrete packets rather than a continuous flow, Planck set the stage for the development of quantum mechanics. His work provided a new understanding of atomic and subatomic behavior, one that continues to influence both theoretical physics and technological innovation today. Through Planck's constant, we gained access to a universe where energy and matter are governed by fundamentally different principles than those that govern the macroscopic world. This shift not only solved a specific problem in radiation theory, but also marked the birth of the quantum age, shaping the future of science and technology. Max Planck's introduction of the concept of quantization of energy, exemplified through his constant H.T., fundamentally altered our understanding of the microscopic world. Before Planck's work, classical physics, which relied on continuous models of energy and matter, had dominated the scientific community. However, it began to show cracks when applied to phenomena at atomic and subatomic scales. The failure of classical physics to explain certain behaviors, particularly the problem of black-body radiation, led to the development of a new framework that would forever change the direction of physics, quantum mechanics. The black-body radiation problem was one of the most significant challenges classical physics faced. Classical theories, like the Rayleigh-Jeans law, predicted that as the frequency of radiation increased, so would the intensity of radiation, leading to an infinite amount of emitted energy at higher frequencies, a prediction that did not match experimental observations. In reality, the energy emitted by a black body reached a peak at a certain frequency and then rapidly decreased, a phenomenon that classical physics could not explain. This discrepancy, known as the ultraviolet catastrophe exposed a fundamental flaw in the classical understanding of energy and matter. To resolve this issue, Max Planck proposed an innovative solution in 1900. Rather than treating energy as continuous, he suggested that energy was emitted or absorbed in discrete units, which he called quanta. This radical idea was a sharp departure from the classical assumption that energy could vary continuously. Planck's hypothesis was that energy was quantized and could only exist in fixed amounts. The energy, E, of each quantum was directly proportional to the frequency, F, of the radiation, with the constant of proportionality being Planck's constant, HA. The equation E equals h c.f became the cornerstone of his theory, and in doing so, Planck introduced the first explicit representation of quantized energy, which laid the groundwork for the quantum revolution. Planck's work on blackbody radiation and his introduction of HA resolved the ultraviolet catastrophe and provided a correct explanation of the radiation spectrum. However, while the mathematical model solved a specific problem, it also raised profound questions about the nature of energy itself. For centuries, the concept of continuous energy had been integral to classical physics, and the idea that energy could only exist in discrete packets was challenging and counterintuitive. Nonetheless, Planck's constant, h, became an essential feature of the new quantum theory, which was further developed by later scientists. Although Planck's quantum hypothesis was initially met with skepticism, its validity was demonstrated through subsequent experimental results. One of the most significant developments following Planck's work came with Albert Einstein's explanation of the photoelectric effect ***. Einstein applied Planck's concept of energy quanta to explain why light of a certain frequency could cause the ejection of electrons from a metal surface, while light of lower frequencies, regardless of intensity, could not. Einstein's use of Planck's quantization theory for explaining the photoelectric effect was groundbreaking. His work showed that light could behave both as a wave and as a particle, a concept that became known as wave-particle duality. This duality, which emerged from Planck's constant, was a central feature of quantum mechanics and transformed how scientists viewed the nature of light and radiation. In addition to Einstein's contributions, Planck's work laid the foundation for the development of quantum mechanics Niels Bohr building on Planck's ideas, used the concept of quantized energy levels to explain the discrete spectra observed in hydrogen atoms. Bohr's model of the atom, which incorporated Planck's theory, described electrons as existing in specific orbits with fixed energy levels. These energy levels could only change in discrete amounts, supporting the idea that energy is quantized. This was a radical departure from classical models, where energy was thought to vary continuously. Furthermore, Planck's constant also paved the way for the development of the Heisenberg uncertainty principle, and Schrödinger's wave mechanics both of which are key components of quantum theory. The uncertainty principle, formulated by Werner Heisenberg stated that certain pairs of physical properties, such as position and momentum, cannot be simultaneously known to arbitrary precision. This uncertainty was a direct consequence of the quantization of energy, as proposed by Planck. Schrödinger's wave equation, which described the behavior of particles as waves, also relied on Planck's quantization of energy. These developments led to the formalization of quantum mechanics, a theory that accurately described the behavior of particles at the smallest scales. Planck's constant, h, is not just a theoretical construct, it has practical applications in modern technology. Quantum mechanics, which was built upon Planck's work, has led to advancements in semiconductor technology, quantum computing, and MRI imaging, among many others. The principles of quantum mechanics are central to the operation of semiconductors, and transistors which are the foundation of modern electronics, lasers, which are widely used in telecommunications, medicine, and entertainment, also rely on quantum mechanical principles derived from Planck's constant. The development of quantum computing promises to revolutionize the field of computation, offering the potential to solve problems that are currently beyond the reach of classical computers. In conclusion, Max Planck's introduction of his constant h not only solved the problem of blackbody radiation, but also revolutionized our understanding of energy and matter. His idea of quantized energy was a radical departure from classical physics and laid the foundation for the quantum mechanics that would follow. The legacy of Planck's constant extends far beyond theoretical physics and continues to influence modern science and technology. From semiconductors and lasers to quantum computing, Planck's work remains central to the scientific advancements that shape the modern world. His contribution to physics is a testament to the power of innovative thinking and the ability of new ideas to reshape the course of science. Max Planck's introduction of his constant, HA, in 1900 marked a pivotal moment in the history of physics, acting as the gateway to a new understanding of the atomic and subatomic world. Prior to Planck's work, classical physics, based on continuous energy and deterministic laws, had been remarkably successful in describing macroscopic phenomena. However, when it came to understanding the behavior of energy and light at small scales, classical physics began to show its limitations. Planck's contribution not only solved a specific problem, blackbody radiation, but also set the stage for the development of quantum mechanics, fundamentally altering our understanding of the universe. The problem of blackbody radiation was one of the major puzzles that led to Planck's breakthrough. A black body absorbs all radiation incident upon it and emits energy in a spectrum dependent on its temperature. Classical physics, specifically the Rayleigh-Jeans law, predicted that the intensity of radiation would increase without limit at higher frequencies, leading to an ultraviolet catastrophe, where an infinite amount of energy would be radiated at high frequencies. This prediction contradicted experimental observations, where radiation intensity peaked at a certain frequency and then dropped off. This discrepancy highlighted the inadequacies of classical theories in explaining high-frequency radiation. To address this, Planck proposed a novel hypothesis that energy is not emitted or absorbed in a continuous manner, but rather in discrete packets or quanta. This idea was revolutionary because it marked a shift from the classical view of energy as a smooth, continuous quantity to a discrete one. Planck's hypothesis introduced the concept that energy could only exist in specific quantized amounts, and this quantization was governed by a new fundamental constant, h, known as Planck's constant ***. This constant served as the proportionality factor between the energy of a quantum and the frequency of radiation, encapsulated in the equation E equals h8hc.f, where E is the energy of the quantum, h.e is Planck's constant, and F is the frequency of the radiation. Planck's constant immediately solved the problem of blackbody radiation by providing a mathematical model that matched experimental data. The quantization of energy explained the observed radiation spectrum and resolved the ultraviolet catastrophe. It was a profound shift in thinking, introducing the idea that energy, at its core, behaves in discrete units, not as a continuous fluid. This insight laid the groundwork for a completely new theory quantum mechanics that would later describe the behavior of particles and waves at atomic and subatomic scales. One of the most significant outcomes of Planck's constant was its influence on the development of quantum mechanics Following Planck's work, Albert Einstein used the idea of quantized energy to explain the photoelectric effect in 1905, further solidifying the concept of energy quantization. Einstein proposed that light, previously thought of as a wave, also behaves as discrete packets of energy, or photons, This work demonstrated that energy and light could not only be understood in terms of continuous waves, as classical theory had suggested, but also in terms of discrete particles, establishing the foundation for wave-particle duality, In the years that followed, Planck's constant became integral to the development of atomic theory, and quantum mechanics, Niels Bohr's model of the atom, for example, used the concept of quantized energy levels to explain the discrete spectral lines observed in atomic emission spectra. Bohr proposed that electrons could only exist in specific orbits with fixed energy levels, and transitions between these levels involved the absorption or emission of energy in quantized amounts, directly tying back to Planck's ideas. This was a departure from the classical view, which held that electrons could occupy any energy level. The introduction of Planck's constant also provided the foundation for Heisenberg's uncertainty principle, and Schrödinger's wave equation two key developments in quantum mechanics. Heisenberg's uncertainty principle states that the position and momentum of a particle cannot both be precisely determined at the same time. This uncertainty is an intrinsic feature of the quantum world, emerging from the fact that particles exist in discrete states and can only be described probabilistically. Schrödinger's wave equation, which describes the wave-like nature of particles, also relied on Planck's quantization of energy, illustrating the deep connection between Planck's constant and the formal structure of quantum mechanics. Beyond its theoretical impact, Planck's constant has had tangible, real-world applications It plays a central role in technologies such as semiconductors, lasers, MRI machines, and even the emerging field of quantum computing Semiconductors, which form the backbone of modern electronics, rely on principles of quantum mechanics that are based on Planck's ideas, lasers, which use the controlled emission of light, operate according to quantum principles, and MRI technology uses quantum mechanics to probe the structure of biological tissues. In the field of quantum computing, Planck's constant is fundamental to understanding how quantum bits, or qubits, behave in superposition and entanglement, offering potential breakthroughs in computational power and problem solving. In conclusion, Max Planck's introduction of his constant h and his concept of quantized energy were revolutionary developments that completely transformed physics. Planck's constant provided the key to understanding the behavior of matter and energy at the atomic and subatomic levels, and it laid the foundation for the entire field of quantum mechanics. His work not only solved the black-body radiation problem but also introduced the idea that energy is discrete rather than continuous, a concept that would go on to shape the development of atomic theory, wave-particle duality, and the uncertainty principle. Planck's legacy extends far beyond theoretical physics, having direct implications for a wide range of technologies that define the modern world, from electronics to medical imaging to quantum computing.